There we go. You probably couldn't hear me before. Okay, so I wanted to do kind of a short stream this morning talking about due dates and talking about algorithms for the create performance task, because I think understanding the algorithms and the expectation of them in your code are one of the biggest challenges in doing the create performance task, other than writing the program itself. And if we don't have good clarification of what an algorithm is and how they're looking at and evaluating it, then we're going to have a hard time missing that mark. So I created a one-page handout that'll be posted in Classroom shortly, and a quick demonstration excuse me, in code.org of what that could look like. And it's a very, very bare bones outline and framework for it. You'll have to fill in a lot, but I'll talk about the process of it. So first thing I want to go over is this quick one-pager of what an algorithm is. I have this up in Adobe Illustrator, but I have the PDF that is attached in Classroom. Or at least it will be attached in Classroom. So the idea is this. So, what is an algorithm in terms of code? I keep doing that. Sorry about that. That's... Okay, that's what I want. An algorithm is a chunk of code that accomplishes a task. I'm just reading from the screen right here. Let me make sure that I've switched over, and I haven't yet. There we go. Okay. So what is an algorithm? What does it mean? So algorithms are chunks of code that accomplish a task. To make sure your algorithm is a little complex and that you demonstrate your programming abilities, the College Board has a couple specific requirements. First of all, it has to be something that you wrote. The entirety of the code you submit as your algorithm should be something that you wrote entirely on your own. You cannot submit code that a partner helped you with, although I think that everybody is doing this on their own, so that's not too much of an issue. All right, so what else? It must contain mathematical and or logical concepts. It's probably going to contain both in most instances. Not every algorithm will have both, but it will have one or the other, and your entire collection that you're going to be submitting will probably have both at some point, and I'll show you what I mean by that in just a moment. So a mathematical concept means code where your app does some sort of mathematical computation, whether it's addition, subtraction, multiplication, division, exponential, percent, whatever it does, or mod. And these are typically used when your program is making a calculation. So even if you're doing a simple game where you're increasing a score, well, that score plus equal 1, that is a mathematical concept. Or if you're saying, hey, you know what, I'm in this game and I got a power up, and it's going to double your score potential, well, that score, times 2. How about if you're doing a food app and you get a coupon? Oh, well, if coupon total multiply 10%. So that'd be a mathematical concept. The logical concept is outlined right here. And it means code where you use a logical or comparison operator. So that has to do with and or statements, not, same as, not equal to, greater than, less than, greater than, equal to, less than, equal to. And that's all these operators right here. And these operators are the ones that you would use in JavaScript. Excuse me, JavaScript. And unless you've told me otherwise, which I don't think anybody has, everybody will be using JavaScript for their performance task. So these are typically used in combination with if statements where your program is making a decision. If score is the same as 10, and when I say same as, I'm talking about the double equal sign. If score is same as 10, set screen to win screen, or whatever it is. Okay, so this kind of outlines expectation, the general expectation of what your algorithm has to have. So it's chunks of code that accomplish a task. And that's pretty much it. I mean, most of your functions are algorithms to a degree, as long as it contains a mathematical or logical concept. Now, there's one additional thing that your code has to do. And in a lot of cases, it's kind of a management issue. And that is this right here. Let me move over my screen. And that is this setup. That your algorithm, your code has to actually have 3 algorithms. And I'm going to try to say this a little bit more explicitly here. Your code should have 3 algorithms. Well, actually, at least 3. But there has to be a setup where you have a parent and 2 children algorithm, and it looks kind of like this. So you have one parent algorithm that manages everything, but then these call on 2 others within this parent. They don't have to be separate; these can be linked, but they both have to be part of this. So, and this verbiage that I have here is directly from College Board. Your selected algorithm must have 2 included algorithms that work in a combination to achieve some result. The best way to think about this is that you have a parent algorithm that requires 2 or more components that can stand on their own as independent child algorithms. So these are things that run on their own, but they run as a result of this. So all these together, working together, do something. Now, that's really abstract and it's really hard to visualize. So I created a kind of bare bones example here. So let me switch over to a code screen here. All right, so this is pretty much how it would look if you're writing it in your in AppLab. And I'm going to make this just a little bit larger, and I'm going to kind of outline a couple of things and talk about what this is doing here. So, as of right now, I have a couple different screens. I have a start screen with an event. I have a game screen. And just to be clear, I didn't write a program here. There's no program that runs, but I did write a couple functions and algorithms that will demonstrate the idea and framework of what you have to create. Game screen, a win screen, and a lose screen. So I have 4 screens created. Now in my code, what I have is, I'm going to show this as text. I think it's a little bit easier to see this way for right now. I want to make sure that these sit on their own and it's easy to see them. So my main function, my parent function, is this play game function. This is my main algorithm. And I'm calling it right here. So in this algorithm, this thing that runs, it is calling on 2 other algorithms. And these are the children. So the first one is set board. And look, I have a logical concept or mathematical concept. I'm setting these equal to 3. I'm setting the board. Down here, I have another algorithm, which is function check win. So I'm going to be checking to see if somebody wins. Actually, I should have this just, I'm going to change this for check end game. And then we're going to do check and game. Okay, that probably makes a little bit more sense labeled that way. So checking for the end of the game if the lives are the same as 0. Set screen to lose screen if score is the same as 10. Set screen to win screen. So all these are working together for the overall game. Now I'm missing a lot of code here because I'm trying to show you the framework of just the algorithmic part. So once again, check function play game. I'm setting the game screen, and I'll be doing a bunch of other things here. If I add a sprite, maybe I could do a random number between 200 and 400. And I would say set sprite. This isn't the real code, but equals something like this. If position is greater than 250. I know I'm kind of getting off track here. Something dumb like that. Okay, but the whole point being that I still have this main parent that's controlling a lot of stuff in the game. But still, for the full game to function, it has to depend on these two children that are called in here. So parent, and then children. Logical function, mathematical function. Okay, so that is one of the cores of. That's one of the cores of what they're looking for within your code. So the algorithms, and there's one other thing that they'll be looking for, and that is abstraction. And abstraction has to do with managing complexity, and I'll probably do a completely separate thing for that either tomorrow. Actually, let's do Wednesday, where I'll specifically talk about abstraction. But abstraction's a lot easier because this in itself is abstraction. Okay. And one other thing I'm going to show really quick. I'm going to go back to Grumpy Cat that I had talked about last Friday, I believe. Let me get back to that main screen here. And let's talk about algorithm again, and we're going to talk about it really quickly within the example program that they had listed here. So here we go again. So let's see if we can identify the children and parents. So right here, function reset game, welcome screen, starting values. So right there, we know that we have an algorithm. Starting values is part of this. Update screen is part of this. So right here, this is the parent. And right here, we could probably consider these the two children. On event, go to score, click function set screen. So they could have pointed to this, but for this, they're actually showing this. So this would be the parent algorithm right here. Handles all purchasing behavior, even though they have a spelling error, but it's not a big deal. So the main thing they're pointing at is the whole store that they added. And they're probably pointing to this because everything else is almost identical to what all of you did with the clicker game. So this is the main thing that they changed. We have logical operators. We have a logical operator. You have mathematical operators, here. Function purchase. And then function set prices. Now let's see how this is linked. Function set prices, update cost. And it's linked basically through here. That's how they're linking it. So they're not linking it through calling an additional function. They're linking it through this right here, which is the cost, the yarn cost. See right here? This is depending on this right here. And then set prices, function set prices. So you have the main one here. I passed it already? Yeah. Sorry, I know this is kind of all over the place. Okay, so once again, this is the main parent algorithm that is managing all of the purchasing behavior. And here's child algorithm 1 that's dealing with all the prices. And child algorithm 2 and the abstraction they're referencing. for doing all of this, which is a little bit interesting because it looks like it's changing color properties, which is fine. It still works the same way. You're going to have to figure out what that setup looks like for your main, for whatever program that you're writing. And let me get back to mine right here. But no matter what, this is still the foundation for it. And I was trying to show a really easy example, because once you're calling on two different functions within that function, there's already dependency. They already belong to this because they're being called in there, and they're all working together. This is still the parent. This is still the children. It works a little bit differently than different than the Grumpy Cat one, but the foundation is still there. So whatever you're doing, make sure that this is still the setup. So this is the easiest visual that I could give you that kind of shows the way this works. So only runs as a result of the parent algorithm, only runs as a result of the parent algorithm. This still manages everything else and has to be integral to your overall program, where your program would not run without this. All right, so if I come across any other good examples, I will make sure to show them and share them. If you have any questions, if you want any more clarification, make sure that you're contacting me and letting me know. The district opened up your student accounts, so you now have official district email, which is your student ID number, that 123 number at c-vusd.org, and you can email me directly, and please do so if you have any questions. If any of you are interested in doing any sort of Google Meet to talk more directly as a group, let me know. I might just do that on Wednesday or Thursday anyways, to see if anybody wants to hop on and talk and discuss a little bit about your create performance task. And I think that's going to be just about it. Let's take a look really quickly at our deadlines and see what's going on for this week. So by tomorrow, you should have your project picked. So this was posted a couple days ago. I have all the deadlines outlined. Please make sure that you are following this. So by tomorrow, you should have your project picked, whether or not you're doing some sort of a food app, a game, fashion, whatever that core thing is that you're doing, you should have decided by tomorrow. By Friday, you should have that core algorithm decided. So based on what we discussed today, you should have that main setup. At least be able to draw it on paper. I'm not saying you have it coded, but you know how that's going to work, and what's going to depend on what. And make sure that you have that set and done by Friday, because next week is spring break. You should be working on stuff next week, but there's not going to be any deadlines. There won't be any new content. And the week after, we will be picking up where we left off. So that's going to be it for today, and I'll see everybody in the next stream. Take care. Make sure you stay in contact. Let me know if you need anything. Have a good day. Hope everybody's doing well. All right. And see you later.